Size time in a start. Okay, we will now resume the plenary talk by Professor Sandy Klauscher from University of Ljubljana, Slovenia. This session is going to be chaired by Professor Manoj Channat from University of Kerala. Manoj.
Thank you and welcome. I welcome all the participants for the 20th plenary talk number 20 of the ICNTDM 2020. So the speaker of this talk is Sandy Klauscher, and I have great pleasure in introducing Sandy. Sandy Klauscher is a professor in the Faculty of Mathematics and Physics at the University of Ljubljana, and also he has a position in the Faculty of Natural Sciences and Mathematics, University of Maribor. His research interest into graph. Basically, he works on graph theory and applications. Main topics: domination, other invariants, metric graph theory, graph products, chemical graph theory, tower of Hanoi problems. He has more than 300 papers, and also the books. That is he has 2 books on product graphs, 2 editions, and both are considered to be the very fundamental book on graph products. And another book is on the Tower of Hanoi problems, Tower of Hanoi myths and maths. Again, that is 2 editions. He is now completing the book on domination game, which is a topic of today's talk. He is an editor of Bulletin of Malaysian Mathematical Society, Graphs and Combinatorics, Associate Editor of Discrete Applied Maths, ARS Mathematica Contemporanea, and ADAM, Art of Discrete and Applied Mathematics. And Sandy is, I'm really glad to inform you that we have been in, he's very fond of India. He has been visiting in India several times. I'm fortunate to have worked with him for 2 bilateral projects, and through Sandy, I have been able to collaborate with many of his colleagues in Maribor. So he will be talking on half conjectures and domination game. So it's over to you, Sandy. Please.
Thank you, Manu. So let me start this talk. It is about the domination game and the 1/2 conjectures. As you will see, there are several 1/2 conjectures. In first place, there was only one 1/2 conjecture, but we have a very recent one, a bold one, that might be open new horizons on the domination game. This is mostly joint work with Bujtás, who is staying now for 2 years in Ljubljana. He got a research position here. My PhD student Vesna Iršić and with Kexiang Xu from Nanjing. And one of the results that I will present is about split graphs, and this is from a joint paper with Tijo James and Vijay. So let me just give you first the basic facts and rules about the domination game, so that those that are not familiar with the game can follow the rest of the talk. So what is the domination number? Everyone knows. I will not repeat the definition. And now we have the domination game, which is played by two players. One is dominator and the other one is staller. We address dominator as he and staller as she, and they take turns choosing a vertex in a graph G. And the key point is that whenever they select a new vertex, this vertex must dominate at least one vertex which was not dominated by the previously selected vertices. So formally, this is written like here. So the close neighborhood of the selected vertex must have something which is not in the close neighborhood of the selected vertices. So each vertex must eventually be selected such that one new vertex is dominated, which means that the game will eventually end on every finite graph, of course. We consider only finite graphs. Now the players have different strategies. The strategy of dominator is to end the game as soon as possible, while the staller wants that the game lasts as long as possible. So this is kind of a game with different competitive goals of two players, and one can imagine that there could be also some applications behind it. Now, what is the game domination number? This is the number of moves when both players play optimally, using optimal strategy. And it's a simple argument that this is indeed a graph invariant. So it's really, we can use the notation gamma G of G. This is the case when the dominator has the first move. We call this the D game. And we denote the sequences like D1, S1, D2, S2. And if the staller starts the game, then we use the notation prime, gamma G, prime of G. This is when the staller starts the game. But usually, or in many cases, only the D game is studied. And I will show you the reason in a minute why this is the case. But if we we consider also the S game, then we use this notation with primes, S1 prime and so on. So this game was introduced in the seminal paper in this paper in 2010, and it really made a big impact on the area. So nowadays there is about 100 papers related directly on the domination game or closely related to it. And as Manu said, we are just finishing a book on the domination game that will be published probably next year, most likely 2021 by Springer. So what is the connection between the domination game and the usual domination number? This was, by the way, already mentioned in the talk of Tijo, when he was speaking about Michilsky construction and the domination game. Well, the idea is that whenever dominator plays the game, he can imagine that he selects vertices from a minimum dominating set, which means that the game will end up in at most 2 times gamma minus 1 moves. And of course, when the game is finished, the vertices selected form a dominating set. So clearly, the domination number is a lower bound for this invariant. And anything is possible in between. So a simple example, if we play on a tree, dominator will play this vertex because in this way he dominates already 4 vertices and there is nothing left for staller but to dominate the remaining vertex. This is this one and the game ends here. But now if the staller is the first to play, so she will play here, because then dominator has no way how to finish the game in the next move. he might play here, and Stoller will end the game here, which means that the game domination number is 2, and the Stoller start game domination number is 3. But it can be the other way around. So if the players play on c6, then it's not an advantage for Stoller to start, because if dominators start here, and it's clearly by the symmetry, it doesn't matter where he starts for the optimality of the first move, Stoller can play next to it, and then dominator must still have one move. But if Stoller will start, of course, again, she has no options with respect to the optimality, but then dominator can play the vertex opposite to it, and we have the other way around. So we have that the game domination number is 3 and Stoller start game domination number is 2. But this is the most what it can be, the difference can be between these two games, between the D game and S game. One of the fundamental results of the game is that the gamma g minus gamma g prime in absolute value is at most, the difference is at most 1. Half of this theorem was proved in the seminal paper, and the other half was then proved by Kinnersley, West, and Zamani in their beautiful paper from 2013, where they also introduced the continuation principle. And with the continuation principle, the proof of this result is then simple. But in the first half of the proof, when we gave it, was quite complicated. So for this, I will now show you the continuation principle. And for this, I need the concept of a partially dominated graph. So what is a partially dominated graph? This is a graph together with a set S of vertices, which is declared to be the set of vertices already dominated. So you don't need to dominate these vertices to end up the game, but you can play these vertices. It's no problem. You can play such a vertex if something new is dominated. If there is something in the neighborhood of a vertex from the set S not yet dominated, the player is allowed to play such a vertex. And we denote by G bar S the partially dominated graph as just described. And the number of moves played on this graph is just the same as before. So gamma g and gamma g prime are defined as before. This is the D game, and this is gamma g prime for the S game. Now the continuation principle says that your intuition is correct in this case. In this case, I emphasize this because there are several instances when intuition is not correct for the domination game. It turns out that what you think it should be true, it's not true. But in this case, it is true. So what's intuition here? Intuition here is that if you have the following situation, that the set B is a subset of set A, then the game on the partially dominant, on a bigger, so if you declare more vertices to be dominated, then you need less moves, or at most equal number of moves, to finish the game as if you declare some subset of the dominated set A to be already dominated. And it's the same for S game for gamma G prime. Now, okay, let me just give you very quickly a brief idea, because this is one of the key tools that is used in the area. And it's the continuation, it's the imagination strategy. It was introduced in our seminal paper, and we borrowed, I mean, we got this idea from the theory of the coloring game, where also the imagination strategy is used. So the idea is the following. So imagine, dominator imagines that there are two games that are played. The real game, which is the game on G bar A, which is the real game, and real game means that they are actually playing. And the other game, game B, is the one that is only imagined by dominator. So Stoller has no idea that there is some such a game, but dominator will imagine some moves of dominator in the imagined game and some moves of Stoller in the imagined game. And now the setup is such that in the real game, Stoller will, of course, play optimally, because this is what she is supposed to do, because this is the only game she is playing. and dominator maybe not, because dominator will play optimally in the imagined game, and of course Stoller might not, because dominator has no idea what Stoller wants to do in the imagined game. And now in this setup, this imagination strategy is quite simple, but it can be made more involved in different circumstances to get different results. So dominator just wants to keep the rule that the set of vertices dominated in game A is always a superset of vertices dominated in game B, because this is our original setup, and then he will just keep this rule. And how will keep this rule? Well, first of all, he will play a vertex in the imagined game. So, okay, if the game is finished, we are fine. And if it's dominator's move, he selects an optimal move in game B. This is always legal because of the rule. And then he plays it also in game A. He copies his own move to game A, which might not be optimal now in game A, because this is just a copy of some optimal move from the other game. But if this is not legal, and this is actually the point where this imagination strategy can be very tricky, the moves might not be legal when copying from one game to the other. So then you need to do something smart or not so smart. In this case, not so smart. In this case, dominator can just play any undominated vertex, because then this will just keep the rule. And now if you think a little bit about, I don't want to go into more details, but then because dominator is playing optimally in the imagined game, in game B, this means that Stoller maybe not. So this game can be even longer, can take more moves than what was done in this setup. And in the real game, Stoller is playing optimally, but dominator not. So maybe if dominator will play better in this game, it could be even faster. So you end up with what you want. So you end up with these two inequalities. And when you have these two, this principle, when you have this continuation principle, then you can easily prove the theorem that I said. It's that the difference between the D game and S game number is at most 1. So you just play the D game, and then you consider G prime to be the partially dominated graph after the first move of dominator. And then clearly the gamma G of graph G is not more than gamma G prime on this graph plus 1, because this plus 1, this is the first move. And then this is just definition. Yes, they will play the game on the Stoller will have the next move. And this is partially dominated graph, so they will need to finish the game like that. But now you have the continuation principle that clearly gamma G prime on G prime is not more than gamma G prime on G. And then you put this together and you get this plus 1. And by a parallel argument, you get the other inequality. So you just consider the S game and you get this inequality. Okay, now let me pose now the 3/5 conjecture, also already mentioned by Tijo in his talk. This is the conjecture. I put it both for the tree version and the general version, but maybe let's just consider the general version. It says, so you focus only on the D game. It says that if you have a connected graph, then the game domination number is not more than 3/5 of the order of the sorry, here it should be G, yes, and here should be G. So here we are talking about graph G. So this is the 3/5 conjecture, and they are not equivalent. So one would say if you can prove it in general. So the point here why it's not the conjecture. So of course, if you prove it for any connected graph, you prove it for forests. For trees, but the other way is not true, because the point is that here intuition is false, and the intuition that is false is the fact that the spanning graph can have smaller game domination number than the original graph, which is definitely not the case for the domination number, because if you have a spanning subgraph of your graph, the domination number will definitely be at least equal, if not bigger, because if you remove just some edges, then of course you need at least that many vertices for the original graph to dominate the spanning tree, spanning subgraph. But this is not the case for the domination game. But anyway, so this is, you should remember this one, 3/5 conjecture. Now, if this conjecture is true, it is sharp. And here, for instance, you have the list of all trees on 20 vertices which attain the equality. So this is the complete list on these two slides. These guys and these guys. So these are the 3/5 trees on 20 vertices. And there is a conjecture around which are exactly the 3/5 trees in general. There are some infinite families, and it is believed that these are exactly those trees that attain the 3/5 bound. Now, attacking the 3/5 conjecture, the main tool is Bujtás approach, which is kind of a discharging method, and it was used in a very different ways, but the basic idea is the following. So at some moment of the game, you have three types of vertices. You can have more types, you can have more values for colors, but in this setup you have, let's say, white, blue, and red vertex, and then at each step of the game you assign a value 3 to a white vertex, blue value 2 to a blue vertex, and value 0 to a red vertex. It can be more colors, it can be different numbers here, and it can be very strange numbers here that are guessed somehow by linear programming and so on. But this is the key idea of Cila. And then what you do the following, you consider the residual graph, and the residual graph means that you remove red vertices because vertex is red if it's dominated and all its neighbors are dominated. So this means that the red vertex has no effect whatsoever on the remaining of the game. So you can just destroy it. And if you have two edges between blue vertices, it's also not important. So you can delete this edge between blue vertices. So this is the residual graph. And then Cila proved the following result, that if you have an n-vertex isolate free forest, which has W white vertices, B blue vertices, and now to leaves at distance 4, then this is the case, that the gamma G of a treaty is at most that many. And when you start the game, you just have all vertices white, so you get 3/5 bound from here. So this is very quickly and very roughly the idea of this approach of Cila. Now with this approach, much more complicated, she was able to prove the following theorem. So if the minimum degree is at least 4, then the game domination number is this rational function of delta times n of g. And this is always smaller than 3/5. And for delta is equal to 3, if minimum degree is 3, then you can actually have like explicit number like here. I mean, you can, of course, do it also here. You plug in every delta. But for delta 3, you get 0.55 and so on, which is less than 3/5. And then Henning and Kinnersley followed by a nice, beautiful proof that if the minimum degree is at least 2, then the game domination number is not more than 3/5. So they proved the 3/5 conjecture for graphs with minimum degree at least 2. So the conjecture is now open only for graphs that have pendant vertices, right? So you have connected graphs and delta equal to 1. And the most general result, the best general result is the following, just published by Cila very recently. If you have an arbitrary isolate-free graph, even need not be connected, then the game domination number is not more than 5/8. And 5/8 is just slightly more than 3/5, yeah? So it is 0.625. comparing to 0.6. So this is the best general bound known so far, just published. Okay, now let me go to 1/2 conjectures, the main topic of this talk. And it all started with Rall's conjecture, which was around for quite some time. So I say here actually much earlier. And this 2019 only refers to a paper in which it was stated the conjecture for the first time explicitly. But we knew this conjecture for already several years. And the conjecture is that if you have a traceable graph, that means a graph that contains a Hamiltonian path, then actually the 3/5 bound can be improved to 1/2. The game domination number is not more than 1/2 the order of the graph and floor. Ceiling. Now, what is the conjecture? What is the motivation for this conjecture behind? Well, here it is. So you have a very non-trivial result, which says what is the game domination number of paths and cycles. So you can read it here, and you see here that it is just the equality here. It is the order over half and ceiling of it. If the order of the path is not congruent 3 mod 4, so in 3/4 of the cases, this is attained, this bound is attained. So, and here it's really important, so much non-trivial. This is so this result was proved in an unpublished manuscript. So the West, Zamani, and Kinnersley wrote 2 papers, but one was never published. But in the other one, they also obtained this result. And this result of Koshmaru from 2017 is the only published paper, so in which he gives this result and a little more. So he gives some more information about strategies of dominator installer, how to play optimally on paths and cycles, and some other related results he gives in the paper. So what I want to say is that the domination game is difficult, right? So even for paths and cycles, very simple graphs, it is non-trivial to determine the game domination number. Now you see, here is the motivation for duck. If this is the case, so well, paths are the most simple traceable graphs, right? But how every other traceable graph looks like? Well, every traceable graph has a Hamiltonian path. So we can imagine that a traceable graph is nothing but a graph obtained from this path by adding some edges to it, right? Well, so would this just prove Rall's conjecture? Well, not really. Not really, because again, your intuition here is not what you would expect. Again, this is basically the same stuff that I said before when you consider spanning subgraphs, that the things can go differently than you expect. But here I give you an explicit example. So you start with the P11, which is a traceable graph, and its game domination number is 5. Okay, good. So now suppose we consider some arbitrary traceable graphs on 11 vertices. Well, how you get it? You get it such that you add some edges to P11. And if you add 1 or 2 arbitrary edges to P11, we have checked by computer that the value remains the same, that the game domination number is still the same. But if you consider these 2 guys, so you add these 3 edges, like these 3 edges on like that, or these 3 edges like here, then suddenly it turns out that the game domination number of this guy, let's call it R11, it's equal to 6. So you went up, and now maybe if you add somewhere 1 or 2 more edges, it might go to 7. Well, it doesn't, but maybe it could go to 7, which would be a counterexample to your conjecture. So this approach doesn't work for proving the conjecture. And we believe, but we don't have an argument yet, that if you extend this path for an arbitrary number of, so if you start with path on 4k plus 3 vertices, then this would be an infinite family there where this happens, that when you add 3 edges, the game domination number goes up by 1. So the next result, which supports the 1/2 conjecture of Rall, is that it's true for all unicyclic traceable graphs. Well, how does it look, unicyclic traceable graphs? It has one cycle, right? It's connected because it's traceable. And if you have now two-pendant trees attached to this cycle at distance more than 1, this will not be traceable. Because if you remove these two vertices, two cut vertices where these trees are attached, you get 4 connected components. So it's not traceable, which means that unicyclic traceable graphs is obtained from a cycle by attaching 2 paths at the neighboring vertices of the cycle, maybe only 1 path. I mean, 1 path can be empty. So actually here, when I say unicyclic traceable graphs, this means cycles. We call them tadpole graphs and two-tailed tadpole graphs. So I already said, for cycles, it's a non-trivial result. What is the game domination number? So you can imagine that it's not very easy to prove that the conjecture holds for tadpole graphs and two-tailed tadpole graphs. So that's why we call it a theorem. And we have some computer support also in addition to that. We have checked by this approach, adding some vertices, 2 additional edges or 3 additional edges. Here are details. So if you add 2 additional edges to paths of length between 4 and 21, nothing is wrong. And if we add 3 edges, and you can see that this is kind of limitation that we have by computer for how far we can reach these computer experiments to check the conjecture. And here we did, in the second part of this proposition, we did the same for the cycles. And if we add 2 edges to cycle, or we add 3 edges to cycle, it is again just fine. So no counterexample was found to this conjecture. Now, the next result, and it was actually in this paper that the conjecture was stated for the first time, so that 2019 year is from this paper with Tijo and Vijay. We proved that if you have a connected split graph, then the game domination number is not more than now floor of order half. So which means that this is the conjecture is of course true for all traceable split graphs. So what's the basic idea? Let me just show you quickly. Okay, so we have a split graph. You know, we have a complete subset that induces a complete graph, an independent set, and some edges in between. And if you have now a vertex in the first case, if every vertex from the complete set has at most 1 neighbor in the independent set, then you just start on the complete graph, any vertex from the complete graph, which has a neighbor in I, because if there are no neighbors in I, you have just the complete graph, which is trivial case. And now later on, only the vertices from the independent set must be dominated. So later on, only 1 vertex will be dominated, and you get this then easily that the game domination number is that the number of moves is that many. And in the second case, if you have at least 1 vertex, let's say x1 with 2 neighbors in the independent set, then dominator starts with playing a vertex d1, and then Stoller must play, I mean, it's not necessary, but by the continuation principle, we can assume that Stoller plays optimally by playing a vertex some yt. And now we have this set for 4 vertices, x1, y1, y2, and yt, which were already dominated, and they are, we could consider them as elements of the residual graph. They can be removed from the graph. So we get that the game domination number is not more than 2. This 2 comes from the first 2 moves, d1 and s1. And the game domination number of this partially dominated graph And by denoting G prime the graph when these four vertices we remove, we can use the continuation principle. And the point here is that we have now removed four vertices from this graph, and then we can apply induction hypothesis. So we checked in the beginning, so I didn't point it out here, but here you see, here we checked all small split graphs between 2, 3, 4, 5. So we checked for four orders. And the reason is here that we want that the induction goes back by 4. So we need to check enough initial terms that the induction can be applied. So now you do that, you apply continuation principle, and you are done. And as the last result about this 1/2 conjecture of Rall, let me tell you that the result is also true for all diameter 2 graphs. So if a graph is of diameter 2, then this is true. And even more, the equality holds here. So we have equality here if and only if G is one of these 7 sporadic graphs, and you see these graphs have all order 5, 4, 5, or 6. And there is no equality for 7, 8, and 9. And the only remaining graph that has that achieves equality here among diameter 2 graphs is the Peterson graph. So in a way, this theorem can be understood as in fact a characterization of the Peterson graph. Because, I mean, these are small graphs. They have 6 vertices or more or less, 6, 5, and 4. So these are really just sporadic examples. But after 6, there is nothing but the Peterson. So you could say that among diameter 2 graphs, the Peterson graph is the only non-trivial graph that achieves the 1/2 equality in the 1/2 conjecture. Now, maybe I just show you very quickly the idea of the proof. So we distinguish 2 cases, whether we have a vertex of small degree and whether we don't have such a vertex. And this case is quite easy, because what you really need to infer only is that if you have a vertex of diameter 2 graph, then its open neighborhood is a dominating set, right? Just think of a BFS tree from this vertex. So the open neighborhood will dominate the whole graph, which means that the game domination number is, and the domination number is not more than delta. And we already mentioned this upper bound in the beginning, so now we use it, that the game domination number is not more than 2 times domination minus 1, and we get what we want. And a little more difficult case is if we don't have a vertex of small degree, and small degree means order over 4 plus 1. And then we have this lemma, which says that if we want to dominate the rest of your graph in a diameter 2 graph, then we don't need more than 2/3 of the number of vertices yet to be dominated. And here again, you prove it. So the idea of this lemma is that whenever a dominator is to play, he can always dominate at least 2 vertices. That's the key idea, because if you have diameter 2 and if there are at least 2 vertices not yet dominated in the game, then if they are at distance 1, you play any one of them. I mean, each is a good move for dominator. And if they are at distance 2, then they have a common neighbor. So dominator can play the common neighbor. So in any case, dominator will kill at least 2 vertices with its move. And then the rest is just a computation, depending who ends the game and so on, and you end up with this, what is written here. Okay, and now when you do that, you just get this corollary. You can state this result in terms of the maximum degree. The gamma G is not more than this bound. And then the proof goes like that. The case is if you have a vertex, universal vertex, or a vertex that is adjacent to everyone but one vertex, are very simple because you need only 1 or 2 moves to finish the game. And in the other cases, dominator starts the game on a maximum degree vertex, and then by applying the lemma, so playing in the way that he will dominate at least 2 vertices in each of the subsequent moves, we get this chain of inequalities, and this is what we wanted. Now, the real work here is then the proof that the equality case is basically attained only by the Peterson graph and these small 7 sporadic cases. And for this, we have a nice lemma, which I don't want to say it here explicitly, but this lemma basically says that how much in average dominator can achieve in subsequent move of the game. So this, in the first move, he can definitely play a greedy strategy. So he will play greedy strategy, meaning that he will always dominate such that at given moment he will dominate as many new vertices as possible. So, and Stoller will always dominate at least 1, but this is then just by obtained by this inequality by double counting and by averaging the number of vertices dominator can dominate in his subsequent move. And now how the proof works for the equality case. Well, very briefly, the cases up to 10 were checked by computer, and here we got these 7 sporadic cases and ruled out all the other graphs but the Peterson graph. And for the cases when n is 11 or more, again, for 11 we distinguish 2 cases, and we use lemma B, and this lemma gives that the U2 is not more than 2, which means that after the second move of dominator, there will be only 2 more vertices yet to be dominated, so the game will be ended in at most 2 more moves. U2 was the 3rd move of the game, so not more than 5 moves will be played, which is fine. And for n between 11 and 14, you can use the same approach with a little more work. You can obtain the same. And in the general case, now assume that n is at least 15. So now we want to show that there is no equality case among the amateur 2 graphs. Now what you get is if you use lemma B, you get U1 is whatever it is, U1 prime is whatever it is, so this is simple. And lemma B gives you that U2, so the number of vertices yet to be dominated after the second move of dominator is this rational function. Okay, and now we use lemma A, which says that after that, dominator will kill at least 2 vertices in each of his subsequent moves, which means that when you plug these together, that the game will be finishing at most that many moves, and we want to show that this number is not more than n½. And this is equivalent to that this polynomial 3n² minus 40n8 plus 52 is positive, and this is valid for all n equal at least 15. Now you see here why the cases up to 14 were needed to treat it separately. Now to finish the talk, let me present the very fresh new general upper 1/2 conjecture, which we we have a little better bound for the amateur 2 graphs up to from on 11 vertices. You can subtract this one, and there are equality cases. But now let me give you the general 1/2 conjecture, and this is this one. That we posed with Chila and Vesna not long ago. I mean, we were thinking about it for a while, quite a while, and we kind of, it was somehow around, but as Doug Rall would say, it's really bold conjecture. Now we conjecture that if delta is at least 2, then actually the correct bound is 1/2. So remember, it was proved the 3/5 conjecture, one of the main results about 3/5 conjecture is that if delta is at least 2, so this condition, then gamma g is less or equal than 3/5 times ng. But now we conjecture that it's less or equal than 1/2. And we have some support for it, but suppose that it will happen that someone will find a counterexample, then we have also two weaker conjectures. So one weaker conjecture is that maybe if this is not true, maybe there is some universal constant C such that you can add it as an additive constant here in this bound that holds for all graphs. And even a slightly weaker conjecture is that instead of having 1/2 here, we claim that there could be a constant which is strictly smaller than 3/5, and it's still true. But okay, so these are kind of background conjectures, but this is really the 1/2 conjecture that is now that we want to emphasize. Very quickly, we can prove that this conjecture is true for claw-free cubic graphs. If G is a claw-free cubic graphs, then this is the case, which is highly non-trivial result. You can maybe imagine that this is really not simple. And for arbitrary claw-free graphs, not cubic, so here we have cubic. For arbitrary claw-free graphs, we have a little worse bound, 11/20, but this is definitely smaller than 3/5. And maybe the most difficult result is this one. We can prove that if G is a traceable line graph, so arbitrary traceable line graph, then this is the case. And this also is the most general, the most non-trivial class of graphs for which Rall's 1/2 conjecture is proved. You see, this is just traceable line graph, and we can prove that it is at most the order over 2. And we have also checked by computer that there are no small counterexamples, so it holds for at most 10 vertices. And we have many equality cases, and here is just a list of equality cases. We have, for instance, let's say 5 equality cases of order 9, and these are drawn here, these 5. And these are 2 sporadic examples of order 30 that attain the 1/2 bound, and the minimum degree is at least 2. And here I will stop my talk, and I thank you all for your attention.
So thank you, Sandy, for your nice presentation. Is there any questions, comments in the audience, or you can also chat in the chat box.
Sandy, you mentioned about Silla's recent result for G is a claw-free graph. Gamma
Yes.
G less than or equal to ng/2.
Yes.
How close are they, the values? Any information is possible?
Yeah. It is sharp. It is sharp for this also. Yeah.
So there are graphs with the gamma G is equal to ng/2, isn't it? Yeah,
Yes.
Yeah.
So this 1/2 conjecture, the settle the conjecture, is it very far away, or you have in general?
Manoj, there is a question in the chat box.
Yeah. So it is. There are not so many equality cases. Yes, we would like to have some infinite families, nice infinite families for the equality. We have some ideas. Actually, Rall came with one not long ago. But this conjecture really says that there is a big difference between graphs with degree at least 2 and graphs having dependent vertices. Because for graphs having dependent vertices, we have many examples where exact value is 3 or 5.
Okay. So there is a question from Venkatesh Raman. Are there any algorithmic results? I would expect that some game domination number will be harder than the domination number. But what about for some simple classes like trees?
Oh, yeah. So we believe that the game domination number is difficult also on trees. So we know the domination number on trees is easy, I mean, it's polynomial. But the game domination number, we believe it's difficult already on trees. But we don't have a proof of it. So it's a nice problem for working on computational complexity to prove that the game domination number would be space complete, for instance, on trees, in the case of trees.
There is another question from Meenu Mohan. Is there a way to define domination number for directed graphs? What is different from that of undirected graphs?
Yeah, there is something which is also called domination, game domination number, that has something to do with directed graphs. It's a different story. This was introduced by Noga Alon, author, also some time ago, but not studied a lot. But in this context, we are doing, this was not yet studied, the domination as such in diagrams. But it is a legal question that makes sense. Yeah. Have domination well defined the digraphs, you can play the game on digraphs, but this is yet to be investigated.
Okay, so there's another question from Nagaraj Armugam. What is the motivation of game domination?
Okay. So we had several motivations behind. So as you know, domination is motivated by some applications that we want to put locations in a network in a good way, and you want to put fire stations or whatever. But now you can imagine that there are two competitive, so one politician would like to do something like that, and the other politician wants to do it just the other way around, and they compete like that. So this was one thing that we had in mind, that there are two competitive players who want to dominate the graph, but with different goals. So they want to achieve something different. They compete online. And motivation was also a coloring game, because coloring game is a classical game, and we figured also that might be interesting to consider domination. And something else, yeah. These two motivations are original.
Okay. So let us thank Sandy for his nice talk once again.
Okay, so I will stop sharing the screen now.
Okay, thank you, Manoj and Sandy. So we'll reassemble at 16:15 for the plenary talk by Janos Pach. So we have 30 minutes for the next plenary. Thank you.